Hello, everyone. Welcome once again to a TVS colloquium. Today we have the pleasure of having Susmita Das. She's a postdoctoral fellow, at IUCA, and will be telling us about stars from Gaia to Rubin. So please, Susmita, take it away.
Okay. Hello, everyone. Thank you for being here today. Thank you, Priscilla and Fateme, for giving me the opportunity to present my work. I am Susmita, a postdoc at IUCA. Previously, I was at Konkoly Observatory, Budapest. So today I will be talking about BL Herculis stars. So you might not be familiar with BL Herculis stars, but I'm pretty sure almost everybody has heard about Cepheids. Now, Cepheids are of two types. One is the classical Cepheids, which are the younger population 1 stars, and their old counterparts are the type 2 Cepheids. So BL Herculis stars are nothing but the shortest period type 2 Cepheids. Of course, we will be looking a lot more in this talk. So this talk is based on a series of 4 papers that we have published, where we have computed a very fine creep of BL Herculis stars and thereby studied the effect of metallicity and convection parameters on period-luminosity relations. First, in this one, we studied the Johnson cousin bands, so UBVRIJHKLL M. We extended the study to Gaia passbands, and finally, we have extended in our most recent study to include period luminosity relations in the Rubin-LSST filters. So, of course, this is the transients and variable stars group. So the variability tree needs no introduction. However, what I would like to point is we are talking, in this talk, we will be specifically talking about classical pulsators, which belongs to the class of variable stars, which are intrinsic, their cause of pulsation is intrinsic to the star. And if you look at the variability tree, there are, of course, extrinsic variables, intrinsic variables scattered all over the HR diagram. But if you look in particular, the one that is in green, all of these subclasses belong to the pulsation variables. And if you look at this figure, you see that they dominate over the entire variability tree. It is no coincidence because variability, because of pulsation, are scattered all over the HR diagram across different stages of evolution. Now here, if you look, this one is the main sequence, this is the horizontal branch, and the almost vertical strip, which is enclosed in the dashed vertical lines, is the classical instability strip. So once again, this is the HR diagram that represents variable stars, pulsating variable stars across the HR diagram. But what we are looking for are the classical pulsators. So they are the pulsating variables that lie within this classical instability strip. This is characterized by the extension over the entire luminosity range, but constrained over a very narrow temperature range on the HR diagram. The most popular classical pulsators are the RR Lyris, which lie at the intersection of the 0H horizontal branch and the classical instability strip. Next, we have the delta Cepheids or the classical Cepheids, which are higher up on the instability strip because they are intrinsically brighter. And intermediate to RR Lyris and the classical Cepheids lie the type 2 Cepheids. And the different subclasses are BL Herculis, W. virginis, and so on. So when we say intermediate, it means that they are brighter than RR Lyris, but they are fainter than the classical Cepheids. Now the characteristic, the similarity among all of these is that they are driven by the same cause of pulsation. So that is the kappa mechanism that drives the pulsation in these stars. And all of these, the ones that lie within the classical instability strip, follow what is called the period luminosity relation, which we will be looking in a couple of slides later. So now, as we said, we have RR Lyris, classical Cepheids, type 2 Cepheids. Here, RR Lyris are pretty easy to distinguish out because conventionally they have pulsation periods less than 1 day, right? And then we have classical and type 2 Cepheids. Both of these have pulsation periods ranging from 1 to about 100 days. So how do we separate classical and type 2 Cepheids? Of course, at first glance, you see that all of the different types of classical pulsators exhibit different light curve structures. So that is one distinguishing parameter among the different subclasses. The next, as we had seen from the HR diagram, is that type 2 Cepheids are intrinsically fainter than classical Cepheids, which is why it will obey a different period luminosity relation, and thereby it separates out on the period luminosity plane. Now, also because of the mode of pulsation, if the mode of pulsation is different, the light curve shape will be different. For example, for the fundamental classical pulsators, they have a typical sawtooth light curve structure, whereas for the first overtone, they have more of a sinusoidal light curve structure. So why are we so interested in classical pulsators? This is because they obey well-defined period luminosity relations, especially in the near-infrared bands. Here, this is from OGLE. This is from the OGLE survey, and we have period luminosity relations for all the different types of classical pulsators, each depicted in different colors. Now here on the x-axis, we have log P. On the y, we have Wesenheit, which is a pseudo magnitude for the individual passbands. So we use Wesenheit as a combination of typically of 2 or 3 passbands to reduce the impact of reddening correction. So this is a typical period luminosity relation. Although we say luminosity, it actually means magnitude on the y-axis. So if you look here, the first thing that you see is Cepheids and type 2 Cepheids clearly separate out on the period luminosity plane. So this was not intuitive back in the 1950s. So before they were classified as population 1 and population 2, they were, because of course, once again, they have the same pulsation period overlap of 1 to 100 days. So prior to their separate classification, it was assumed that they obey the same period luminosity relation, which led to discrepant cosmic distance scale measurements by Hubble back in 1931. It was only around 1950s when Bade said that there was no a priori reason to assume that two Cepheids which have the same period, but one belongs to type 1, population 1, the other belongs to population 2, should have the same luminosity. And that's how they fixed the different PL relations for population 1 Cepheid and population 2 Cepheids. And as you see, this is the present day PL relation that we have, and they clearly separate out in two well-defined period luminosity relations. The reason, of course, is that type 2 Cepheids are intrinsically fainter than classical Cepheids. So at any given period, classical Cepheid will always be brighter than its type 2 counterpart. The next thing that we see here is that it appears that PL relations obeyed by type 2 Cepheids follow the same PL relation as occupied by the RR Lyrae stars. So this is very useful because typically when we typically use classical Cepheids for extragalactic distance measurements, right? That is the population 1 distance. Now, there can be an alternative distance scale that comprises of RR Lyrae's type 2 Cepheids in combination with tip of the red giant branch. So potentially, this forms the population 2 distance ladder as an alternative to the more conventionally used classical Cepheids. So this is useful because say we have certain clusters where there is a scarcity of classical Cepheids. Say it's older. We have a galaxy which is older, typically older than where classical Cepheids would be present, is where the type 2 or the population 2 counterparts come in handy. So now, why are we so interested in type 2 Cepheids? What does it offer that RR Lyrae and classical Cepheids do not offer, for example? So coming to the motivation of why we are interested in studying type 2 Cepheids. First, we have a brief conventional classification. So, of course, all of these are in different evolutionary stages, but from the observational point of view, the convention to classify them is BL Hers belong to the shortest period pulsation period between 1 to 4 days. W Virginis have pulsation periods 4 to 20 days, and RV Tauri stars have pulsation periods greater than 20 days. So here I would like to point out that if you remember, my talk is BL Hers stars. This is because there is currently, so ideally we would want to compute models of entire type 2 Cepheids. But because of current limitation of the stellar pulsation codes, which can only reliably model BL Hers stars and the shortest period W Virginis stars, is why we have restricted our study to only BL Hers stars alone. Now here I would like to say it's a repetition that type 2 Cepheids are brighter than RLI rays but fainter than classical Cepheids. They also obey period luminosity relations similar to other classical pulsators. However, when we started this work back in 2019, 2020, surprisingly, as compared to hundreds of grids of models that were available for RLI rays and classical Cepheids, there were very few grids of BL Her models, or in fact type 2 Cepheids. The handful of studies that did on the theoretical front were Di Crescenzo, who provided theoretical BL Z relations. Marconi provided theoretical BR relations. Redek, of course, in a series of papers, studied several particular interesting observed type 2 Cepheids. So the two on the top are more like grids, whereas Smollett's would model interesting type 2 Cepheid stars. On the empirical front, again, only a handful of papers. Matsunaga, in a series of papers, studied 26 galactic globular clusters and identified 46 type 2 Cepheids, and thereby studied what is the effect of metallicity on the PL relations. To find out that there seems to be negligible or no effect of metallicity on the PL relations. This was further confirmed from the empirical front in 2017. Now the thing is, if you have attended classical Cepheid talks before, you know that most of the research in this field involves calibration of effect of metallicity on the PL relations. So in a situation like this, if we have such a subgroup of classical pulsators that offers the promise of weak or negligible metallicity effect, it provides us a huge advantage over RLI rays and classical Cepheids, which are known to exhibit strong effects of metallicity, especially at the shorter wavelengths. So this was our entire idea, to study this from the theoretical perspective and try to verify with the empirical results. So now hopefully we agree why type 2 Cepheids are so important. Now coming to the data, first I will be talking a bit about the theoretical data that we have used for this particular study. I use what is called MESA-RSP. So MESA is Modules of Experiments in Stellar Astrophysics, which is an open source code. Traditionally, this is a 1D stellar evolution code. In 2019, from Smollett's 2008, there was a new module that was introduced in MESA, which is called MESA-RSP, where RSP stands for Radial Stellar Pulsation. So this code is very convenient for obtaining bolometric light curves, radial velocity curves, and so on, typical of classical pulsators. Now, before we begin, here is a slide of, do we think that MESA-RSP can reliably model light curves? Because at the end of the day, we want to make sure that we are reproducing the right light curve structure. So on the right is an example of, so the dots are from observations and the solid lines are from computed MESA models. On the right is the example of a bulge RLI ray star. On top, we see it's the light curve structure. On the bottom is the radial velocity curve. and it shows quite a good match even when there is a simultaneous fitting of the light curve and the radial velocity curve. Next, we see a type 2 Cepheid in the bulge. And once again, we see that the blue is an observed and the red is a model. Model seems to do quite a good job, even while trying to capture the bump structure at the right phase location. So now with this, we proceed with our computation. But before that, so there are of course different versions of MESA. The one that we used is this one. So we also keep comparing with the latest MESA-RSP version to make sure that results are still consistent. So here is a table that shows different convection parameters. So if you remember, we said that we study the effect of metallicity, but we also study the effect of convection parameters. Because with pulsation models, the choice of our convection parameters play a huge role in the light curve structure as well as the pulsation period. So what we did was we used the four convection parameter sets as provided by the MESA-RSP paper, which is Paxson 2019. Here we have four sets of convection parameters, and that's what we used while computing our grid of models. Now here we have to understand that if we want to model one particular star, calibration needs to be done. It's not that these four are the ultimate choice of convection parameters, because they are supposed to be used merely as starting points. And then we keep fine-tuning. So whatever is the closest model to our observed light curve and radial velocity curve, for example, we have to keep fine-tuning our calibration, the calibration of convection parameters to make sure that our fit keeps on improving. However, that is not what we do here, because we are not dealing with particular stars, particular observed light curves at the moment, but more of a grid where we study the period-luminosity relation and so on, which is why we have not done calibration. We just use whatever is provided in the MESA-RSP paper, which are these four sets of convection parameters. So now, before we begin with the full computation, because usually nonlinear computation takes a very, very long time. So in order to cut down the computation time, we first have to carry out linear computations. The typical parameters that go into MESA-RSP are first the metallicity, the stellar mass, the stellar luminosity, and effective temperature. So metallicity, so all of these values are typical of what is expected for BL Herculis. So metallicity, we use we use 7 different metallicity parameters. Stellar mass from 0.5 to 0.8, which is typically higher. We also use values which might be higher than what is expected from evolutionary tracks. Stellar luminosity from 50 to 300 solar luminosities. Effective temperature from 4,000 to 8,000, which is actually quite broad, but this has been intentionally chosen so that we can reliably estimate the edges of the instability strip. So when we do all of these combinations over Z, X, M, L, and T, it results in 20,412 models per convection set. And then we have 4 convection sets. So that would be 20,000 into 4, right? So it would be computationally very expensive. So here what we do is we carry out what is called a linear computation. The output of linear computation is that it gives us the edges of the instability strip. For that, what we do is we check what is the growth rate of the fundamental mode. Now here, I missed telling one thing, that BL Herculis stars are observed to be pulsating mostly in the fundamental mode. There have only been 2 first overtone BL Herculis stars observed so far. So for this grid, we use the condition that fundamental mode, we only study those models that exhibit positive growth rate in the fundamental mode. So anything beyond the red edge and the blue edge are the ones that would potentially not demonstrate pulsation, right? So between the red edge and the blue edge is where we have positive fundamental growth rate. Next, we also know that from convention, BL Herculis stars have pulsation periods between 1 and 4 days, which is why we have linear period. We allow a bit of uncertainty between the linear period and the non-linear period, which is why we have about 0.2 from what is the boundary of pulsation period. So here we have the dashed lines here refer to the pulsation periods. So now we have the edges of the instability strip, we have the pulsation period bounds. So whatever is in the region of intersection between these lines correspond to potential BL Herculis models. So as soon as we use all of these conditions and cuts, we are left with some 4,000 models per convection set, which is a huge cut from what we initially started with. So for all of these 4,000 models, we run nonlinear computations. So they are full integrations over nonlinear computations. Okay, so now we have completed all of the runs. But before we accept one particular model for further analysis, we have to make sure that they satisfy certain condition. For this, what we do is we look for the condition for what is called full amplitude stable pulsations. So numerically, that translates to delta R, which is the change of radius from one cycle to another. So we had computed over a total of 4,000 pulsation cycles. So after that, we check over the last 100 cycles and we check, is delta R varying by more than 0.01? What about the pulsation period? What about gamma, which is the average kinetic growth rate per pulsation cycle? So we check that delta R, P, and gamma do not vary by more than 0.01 over the last 100 cycles over the total computed 4,000 cycles. So now I would like to highlight that all of these, so set A, B, C, and D refer to different convection parameter sets. However, we have used the exact same ZXMLT. As you can see, there is quite a prominent effect of convection parameters, because even from here, we see that there are differences, right? There is also not so much in the pulsation period, but there are differences. But most importantly, if you look at set B, the exact ZXMLT fail to satisfy the condition of full amplitude stable conditions because they vary by more than 0.01 over the last 100 cycles. So for this particular example, we choose the models that were computed using A, B, and C for further analysis, but we reject the one that was computed from D. Okay, so now after doing this, the output that we have from MESA-RSP, like I said, are bolometric light curves and also radial velocity curves. But from bolometric light curves, we want to transform them into different passbands. So here is where our bolometric light curve is located. So now MESA-RSP also has pre-computed bolometric correction tables. If not, one can also provide custom bolometric correction tables. Now, using the pre-computed bolometric correction tables, we are able to transform the bolometric light curves to the Johnson-Cousin bands UBVRIJHKLL M, and M. Similarly, we also transform this into the different Gaia bands. Now, Gaia passbands are not incorporated in in pre-computed bolometric light curves in MESA directly. So what we used was we used bolometric correction tables combined with MIST, and this is how the different light curves look like, and the radial velocity curve. Finally, in our most recent study, for the first time, we provided theoretical light curves of BL Herculis stars in the Rubin-LSST bands. So we have a whole range of UGRIZY passbands over a wide range of metallicity, mass, luminosity, and temperature. So I have a quick slide here, which we will discuss in a bit when we are discussing about the model fitting approach. So we used Gaia DR3 for comparing the light curve structure. Here, I would like to highlight that Gaia has 5 subregions: LMC, SMC, M31, M33, and the all sky. However, if you note here, we only have all sky, LMC, and SMC. This is because this is only BL Her stars. This is because BL Her stars have low period. They are 1 to 4. They have pulsation periods between 1 to 4 days. From the period luminosity relation, we know that shorter the period, fainter the star, which is why, because M31 and M33 are much further away, is why Gaia is unable to detect BL Her stars. There are other type 2 Cepheids that are detected in M31 and M33. However, for BL Her stars, all we have are observations in all sky, LMC, and SMC. Coming to the methodology, what we do is, this is what we use for both theoretical as well as observed light curves. For observed light curves, of course, there is an additional step where the raw light curve is phased first. Whereas for theoretical light curves, we already have the phased light curves to begin with. So this is how we phase or fold the raw light curve to have the very nice sawtooth light curve structure folded between phases 0 and 1. So all of the dots are the observed points. Next, we fit the phased light curve with the Fourier sine series of the form as given here. So the input parameters that go here are small m, which is the apparent magnitude, and x, which is the phase or the pseudo time, for example, a proxy for time. The output parameters that we have are m naught, which is the mean magnitude, ak, which is the Fourier coefficient, and phi k, which is the phase coefficient. So now this, of course, is clear. Mean magnitude is what is the mean magnitude of the whole range of the light curve, for example. And ak and phi k are the ones that control the light curve structure. What we do is we redefine the Fourier coefficients to what is called the Fourier parameters. So when we say RK1, so it could be R21, R31, and so on. So say this is the Fourier amplitude parameter. It is defined as a ratio of 2 Fourier coefficients. This is the Fourier phase parameter, which is defined as a difference of phase coefficients. So typically, we use R21, R31, and Phi21, Phi31 because the first two are considered enough to capture the light curve structure reasonably well. Coming to the results, so we of course also have period luminosity relations over all of the different passbands that we have been discussing. So Johnson-Cousin, Gaia, and Rubin-LSST. But for this talk, we have included only the period luminosity relations in the Rubin-LSST passbands. So now on the X, we have log P. On the Y, we have the different absolute magnitude Rubin-LSST bands, R, I, Z, and Y. We have also considered, like I mentioned, we have in the study, we had considered BL Her models that are higher than what is typically considered for the mass range of BL Her stars. So we include both categories, the complete set as well as the low mass set. The arrow downwards, increasing Fe by H. If you look at the downward arrow, it means that the different colored lines, so as we move down, the metallicity increases. Now here, on the shortest period are the RR Lyrae that is pulsating in the first overtone mode. Here in the middle are the RR Lyraes that are pulsating in the fundamental mode. And on the rightmost side are the BL Her models that we have been discussing so far. So two very important results from this particular plot. First, when we study BL Hers, for example, you see that there is no split in the lines. So once again, if there is no split in the lines, it means that there is negligible effect of metallicity. Because when you look at the RR Lyrae counterparts, you can see that the exact same metallicities follow different BL relations, right? So this one is very clear that for BL Her stars, as opposed to RLI rays, exhibit negligible effect of metallicity on the PL relation. The second is that, like we had discussed, is BL seems to follow the same PL relation. So it's a continuous PL relation with the RLI ray stars. So this offers us the advantage of using them as combined RLI rays, type 2 Cepheids, and tip of the red giant branch together can form an alternative, the population 2 alternative to the typically used classical Cepheid distance ladder. So finally, our main goal is to study the effect of metallicity, right? So when we say metallicity effect, we have fitted a linear regression, PLZ, and gamma is the coefficient of the metallicity term. So anywhere where it is 0 means that there is weak or negligible effect of metallicity, which is indicated by the red dashed line. This is the bolometric, and beyond that we have all of the different passbands in order of increasing wavelength. One clear result that we see from models is that beyond G, so anything shorter, so U and B show some effect of metallicity, which is consistent with what has been observed, but anything beyond shows weak or negligible effect of metallicity on the PL relation, including on the optical bands. So typically when we study V band or the I band, so typically RLI rays and classical Cepheids, PL relations in their V or I cannot be used reliably because of their strong effect of metallicity, right? RLI rays and classical Cepheids can only be used reliably, the PL relations, in the near-infrared bands. However, for BL we see that they exhibit negligible effect even in the shorter optical bands. So all of these results that we had been discussing so far were using mean. So whenever we do PL relation, all of these are at mean light. What is mean light? It means that the entire pulsation, because we have a whole variation of magnitude over a pulsation cycle. But when we are studying period luminosity relation, we typically use what is called the mean magnitude, which means that we have averaged out the entire pulsation cycle to one particular mean magnitude. However, because variable stars do vary, they across the whole pulsation period, is why we have to be careful. Not only we are supposed to not only we should not limit ourselves to study of PL relations alone, because those typically handle only at mean light. We also must make sure that whatever models we are computing also do well over the entire light curve structure to convince ourselves that we are capturing the right physics, right? So what we do is we use the robust light curve model fitting approach. So what we did was we used all of the BL models that we have computed, and then we used all of the LMC BL from Gaia. So we are comparing empirical LMC BL from the Gaia and all of our models, right? So what is the one parameter that is very well constrained? It is the pulsation period. So even from observations, pulsation periods are very well known, also from models. So our first condition intuitively should be that the pulsation period from the models and the observed light curve should be very close to each other. For the next, what we do is we compute what is called D, which computes the offset between the theoretical light curve and the observed light curve across a range of parameters. So here you see we have included, so these are parameters that typically capture the light curve structure. So we use, of course, the pulsation period, but the amplitude, the skewness, the acuteness, and like we mentioned, the R21, R31, Phi21, Phi31, which are the first two Fourier parameters. So we compute D for each model observed pair, and we find where is the offset minimized. And wherever we have the minimized D model observed pair is what we call our best matched model observed pair. So when we did this, we found a total of 30, which we call our goal sample. So we had a 30 of distinct model observed pairs. So for every observed star, we give a best match model estimate. So for each of these stars, we are also sort of giving an estimate of what their chemical composition could be, what their mass could be, what their temperature could be, and so on. So if you look here, it does well not only with the classic sawtooth light curve, but also a couple of bump features are being captured well. So now we have the reassurance that our models are doing quite a good job when comparing with the observed light curve structures. So tracing back all of the PL relations that we have obtained so far do make sense. So using all of these model observed pairs, we computed the distance to the LMC, which is within the bounds of what has been previously studied in the literature. So we have a quick summary here where I include that we have computed a very fine grid of BL Herc models over multiple passbands. We have studied period luminosity, period radius. We have found that our theoretical period luminosity relations exhibit similar to what has been shown by empirical results so far about weak or negligible effect of metallicity. This again provides us a huge advantage over classical Cepheids, RL arrays, for example. Now a quick, the last two slides on what is this study? How is this study useful in the context of the upcoming Rubin-LSST? So here, this is what is called the Shoes distance ladder. You are probably familiar already, so I won't go into much detail. So this is the typical population 1 distance ladder scale, where in the first rung, there is the geometric distance determinations, and then there are Cepheids detected here, and then this is how we calibrate the BL relation for Cepheids. Next, the next rung deals with host galaxies where there are both Cepheids as well as supernova type 1a, and so on. So here in the first rung, when we calibrate distance with respect to Cepheids, that is used with, so whatever distance calibration has been done here is going to impact in the further rungs. So one needs to make sure that the first rung itself is well calibrated. So for this, so type 2 Cepheids do not have the brightness, they are not bright enough to be of this use, to be used in this particular distance scale. However, now there is the alternate population 2 distance ladder scale, which is also carried out by the Carnegie Hubble program, where we have the type 2. So these are all the population 1 objects, and we have the counterpart population 2 objects, where our Lyris, type 2 Cepheids, tip of the red giant branch can be used together. Now here, in the first rung itself, if you focus in the first rung itself, type 2 Cepheids can play an important role here by providing an independent check. So whatever distances are being estimated by Cepheids, it is useful to cross-match distances using type 2 Cepheids or other population 2 stars, because once again, whatever is being calibrated here, it keeps on propagating up to the next rungs. So in this context, the role of negligible metallicity effect of type 2 Cepheid comes in very handy. Right now, so once again, this is the exact same plot that we have, gamma, which is the contribution of metallicity. And we have all of these different passbands here. We have, wherever you see WGI, WGY, and WIZ are the Rubin-LSST Wesenheit passbands combined. So now here I would like to highlight that the missing thing that we have with respect to type 2 Cepheid research is a homogeneous determination of spectroscopic metallicity. So it is quite crucial to have a homogeneous spectroscopic metallicity estimates for all of these so that we can verify the PLZ relations also from the empirical relations. So here, all the ones that are in circles, so we have 1994, Matsunaga from 2006, Wielgorski from 2022, and Chung's paper from 2022. So all of these, wherever you have circles, are the empirical results. And wherever we have the stars are the theoretical predictions. So now I would like to highlight that W. virginis and RV Tauri, there needs to be more study for W. virginis and RV Tauri. Other than that, we also need spectroscopic metallicities. But in the context of Rubin-LSST, what is most important is we expect many more type 2 Cepheids to be discovered, right? And then the advantage that we have, so we do not have as many spectroscopic metallicities as we want at the moment. But for type 2 Cepheids, this is not so much of a concern because we find from theoretical predictions that there is negligible effect of metallicity on the PL relation. So even if there is an uncertainty of metallicities, we can still reliably use PL relations in the recommended passbands, not in UNB, because they clearly show significant effect of metallicity, but for combinations that use, so this is Wesenheit GI, Wesenheit GY, and Wesenheit IZ. So these three combinations are recommended because if you look here from different models, they have gamma close to 0. Right? So even if we do not, of course, it is useful if we have spectroscopic metallicities. But even if we do not have spectroscopic metallicities, we can still reliably use PL relations in these recommended passbands only to obtain PL relations for further extragalactic distance estimates. That's it. Thank you.
Thank you so much for presenting this amazing, massive, and very necessary work. So thanks a lot.
Thanks.